Hello everyone. For this tutorial video, I would like to introduce the other part of turbulence, which is turbulent flow with regard to solid objects encased in a fluid. Although solid objects in the middle of a fluid stream will cause turbulence, we can also see that solid objects in motion while the stream itself is not moving also cause turbulent flow. As you may have ever noticed if you rode a bicycle or walked quickly through the air in the atmosphere, as you are creating a disturbance in the way it flows. However, simply having an object in a stream or moving in a stream does not guarantee the flow will be turbulent automatically, because like with the fluid itself, there are factors with solid objects disturbing the flow that will help determine whether the flow is straight line or turbulent. Confusingly, the number that determines this is also called the Reynolds number, even though it is a different scenario than with the fluid alone causing turbulence. The Reynolds number is very similar to the original one with regards to solids and moving fluids, but the only factor that is different is the length of the solid as opposed to the radius of the container when we studied fluids without solids in them. However, this Reynolds number, while partially accurate, does not account for things like the shape or roughness of the object, which is also important. However, the dependence of flow with regards to the roughness or shape of a solid is almost impossible to predict with a formula, and is usually determined experimentally or with trial and error. The other thing that is different about this Reynolds number, besides the slight alteration to the formula, is that you use different results to predict whether the flow will be turbulent or straight line, compared to the study of the fluid without solids in them. If the Reynolds number is less than 1, in this case, the flow will be in a straight line with no turbulence. And between 10 and 1 million, a very broad range of values, the flow will randomly oscillate between straight line and turbulence. And beyond 1 million, the flow will be turbulent with almost no straight line path. As a result of both the inherent thickness of the fluid and the type of flow the solid object experiences, the solid will experience resistance from the fluid, which is formally called drag. The formula for fluid resistance for most objects is fluid resistance equals coefficient of drag times density times velocity times cross-sectional area of the solid all over 2. However, multiplying by velocity alone only works for straight line flow, so if the object moves fast enough to cause turbulence, it will become velocity squared instead, although all other factors remain constant. The drag coefficient is simply a convenient way of expressing all of the complex geometrical factors that you would have to take into account, and as a general rule, the drag coefficient is smaller for object shapes that allow fluids to pass smoothly over them, such as airplane wings or raindrops, and is greater for objects that would interrupt the flow more suddenly, such as the flat side of a triangle or a square box. And a rougher surface, even if the object has the same shape, would also increase the drag coefficient. Although these two formulas work best for most objects on a large scale level, there is an entirely different formula for very small microscopic objects such as red blood cells. In particular, the formula is stated by Stokes' law after the physicist George Stokes, and is stated as drag force equals 6 pi times fluid thickness times radius of object times velocity of object. An interesting consequence of these types of formulas is that since air is a type of fluid, an object will not be able to accelerate indefinitely through it, but rather will be dragged to a constant speed, called a terminal speed, or terminal velocity, when the resistive force of the fluid equals and cancels out the other forces acting on the object. If we also remember from our video on buoyant forces in still fluids, buoyant forces still act on solid objects in moving fluids too. So if an object is falling down through a fluid, the buoyant force always acting up on it will also help slow the fall, especially if the object has a low density. Terminal speed explains why skydivers assume the position they do, because when they spread their arms and legs out, they increase the cross-sectional area as well as the drag coefficient, because their body no longer has a smooth shape, so the air will have a more difficult time moving around it. Now that I've explained comprehensively how fluid flows around solid objects, as well as how an object encounters greater resistance when it moves at greater speeds and causes greater turbulence, we can move on to the final study of fluid dynamics, which is how diffusion of liquids works, including an explanation of both household items and medical scenarios that apply this principle. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.